So we welcome Izabella Lovas. Thank you. It's your turn.
Yeah, so thank you very much for this nice opportunity to speak here. I will talk about the work done together with Anna Maria Kish, Pasko Moka, and Gergely Zorán, and you can find our recent preprint on Archive. So let me start by giving you some motivation. Sorry, for some reason I cannot really go to other slides. So, okay, it's working now, sorry. Okay, so let me start by some motivation and by sketching the problem that you are interested in. So we would like to investigate the localization transition of fermions in the presence of disorder. And in particular, we are interested in the physics of interacting systems in the presence of long-range interactions. These systems have been suggested to give rise to the so-called Coulomb glass phase. And let me start by just listing some of the peculiar properties of these long-range interacting systems. So first of all, close to the localization transition, the screening in the system is drastically reduced. This leads to anomalies already on the metallic side in the transport properties. And now, once one enters the insulating side, then things become even more complicated there. One very characteristic property is the depleted density of states in the vicinity of the Fermi energy. In particular, if one considers the density of states, rho epsilon, close to the Fermi energy, epsilon equals 0, then deep in the glassy phase, this should obey the so-called Efros-Shklovskii scaling, which is a universal scaling. And it is written down here. So the density of states is proportional to epsilon or d minus 1, where d is just the dimension of the system. This is a so-called Coulomb gap behavior. And this behavior is predicted by very generic stability arguments. So we expect this behavior in generic long-range interacting systems. And once one starts to investigate the dynamics, and further interesting things happen. One expects a very slow glassy dynamics, various memory effects, and other interesting things to happen in this localized space. So already from this very brief list, you see that we expect a quite complicated and rich physics in this long-range interacting localized models. But of course, this is a very complicated problem. So it's hard to investigate it theoretically. One possible simplification can be achieved by assuming that the fermions cannot hop between lattice sites. And in this case, we can arrive at a classical limit we can arrive at classical spin glass systems. So these systems are still quite complicated and they offer very interesting and rich phenomena. And it turned out that one can gain a lot of insight from an exactly solvable mean field model, the famous Sherrington-Kirkpatrick model. Just as a motivation for what's about to come, let me walk you through this model. So the Hamiltonian is written down here. Here, this spin variables Si and Sj are just classical spin variables, so they can take the values +1 or -1. And the spins are interacting through these exchange interactions, Jij, which are Gaussian random variables in this case, and each spin interacts with every other spin. So maybe this model is fairly innocent looking, but actually the phase diagram is rather complicated and the properties are rather complicated. In particular, one gets a low temperature glassy phase with free spins. So as the order parameter of this phase, one can calculate the average magnetization at a given site, Mi, for a given exchange interaction configuration, Jij. And then one expects that this average magnetization is 0 at high temperatures, but it can be non-zero at low temperatures due to some spontaneous symmetric breaking. However, since the exchange interactions are random, if we go to different sites, then this Mi will have different sites. So if we take the spatial average of the local magnetization, then we get nothing. We cannot really get a spatial order in this model. So this is not, the spatial average of Mi is not a good order parameter. Instead, one can use this so-called advanced Anderson order parameter, which is the spatial average of mi squared. And this is indeed a good order parameter that takes a non-zero value at low temperatures, but is zero in the high temperature phase. Okay, so we get this glassy phase distinguished by some order parameter. But if we look more closely to this low temperature phase, then actually we find a close analog of this Coulomb gap mentioned earlier, already in this classical spin glass system. We get a so-called pseudogap behavior in the distribution of local effective magnetic fields. What I mean by that is written down here. So this HI, the local effective field at site I, is just the average field generated by the exchange interaction with all the other fields. Now, since these exchange interactions, Ji, J, are random variables, this HI is a random variable itself. So it has some distribution, and this distribution function is called pH. And pH shows a universal scaling deep in the glassy phase, which looks exactly as the Efros-Shklovskii scaling in two-dimensional models. So in particular, for small magnetic field, pH is proportional to H. Okay, so we get this interesting low temperature glassy phase, which can be melted by thermal fluctuations. So it goes away if we increase the temperature. So you can see that if we have an exactly solvable model at hand and we can investigate its properties, then we can learn a lot about the generic things that can happen in a low temperature spin glass phase. So it would be beneficial to do the same thing for the more complicated Coulomb gap phase, where the fermions can actually hop between different lattice sites, and where we can also investigate the role of these quantum fluctuations. So it would be beneficial to have an exactly solvable mean field model for the Coulomb glass phase as well. And in fact, such a model has been suggested almost 20 years ago by these authors. And this is the model that we are going to consider in what follows. And I'm trying to explain this model to you at this slide. So we are considering disordered interacting spinless fermions on a Bethe lattice with a coordination number z going to infinity. The Bethe lattice is a tree graph where each side has exactly z neighbors. This is illustrated here for coordination number 3. Eventually, we will be interested in the limit where each side has infinitely many neighbors. Now, the Hamiltonian that we are going to investigate is written down here. It consists of 3 terms. The first term is just a nearest neighbor hopping. The second term is a nearest neighbor repulsive interaction between the electrons. These delta n's, this delta n here is just the occupation of site I minus the average filling 1/2. So we are interested in the properties of the half field case. Additionally, we also have some random on-site potential, epsilon I times delta ni, where this epsilon I is a Gaussian random variable with variance W as depicted here. So this is the model that we are going to consider. And I'm saying that this is a mean field model for the Coulomb glass. Now we don't have long-range interactions in this model. What we have instead is some non-local interaction between nearest neighbor sites. But nevertheless, the important point is that each electron interacts with infinitely many other electrons in the limit where the coordination number goes to infinity. And you will see that we can recover this universal Coulomb gap behavior in the system. Another thing you might notice is the strange scaling of the hopping amplitude and the interaction strengths with the coordination number. And we scale T and V in such a way in order to ensure that the mean field approximation actually becomes exact in this model, but in such a way that we will still have a very interesting, far from trivial physics in the model. Okay, so this model was suggested in this paper many years ago, and the authors also argued that there is an emerging glassy phase in this model at low temperatures. And moreover, the phase transition towards this glassy phase is actually a structural transition, meaning that the transition is not really governed by the external disorder, even though we have disorder in this Hamiltonian. Instead, the transition is governed by the interactions themselves. So it takes place even if there is no disorder in our model whatsoever. Okay, and so this model can actually serve as a mean field model for the Coulomb glass. What I mean by that is that if we consider this lattice Hamiltonian and we are only interested in single site properties, then we can actually perform an exact mapping to a single site action in this case. So the so-called dynamical mean field theory is exact for this model. What this dynamical mean field theory does is that it neglects all spatial fluctuations, but nevertheless, it retains all fluctuations at a given site. You will see more about this later. And this model is a good mean field model for the Coulomb glass, which is completely analogous to the Sherrington-Kirkpatrick model, which is a mean field model for spin glasses. In fact, if one here sets this hopping t to 0, then one can show that this model is exactly equivalent to the Sherrington-Kirkpatrick model. So in this classical case, without electron hopping, we actually recover that very well-known spin glass model. Okay, so in the rest of the talk, I will be interested in the quantum solution of this model. Of course, many studies have been performed to investigate this Hamiltonian, but most of those studies applied quite restrictive approximations. One thing that one can do is to consider the classical spin glass limit where there is no hopping. This is essentially the Sherrington-Kirkpatrick model. Another approach one can take is to focus on the vicinity of the phase transition and apply some Rondeau theory. But again, so this cannot really access the solution deep in the glassy phase, which will be actually the main focus of this work. To obtain this solution, we apply a number of numerical ingredients. I will just briefly list them here, and then I will talk about some of them in more detail soon. So we perform the disorder averaging with analytically with the so-called replica trick. Then we perform this exact mapping to a single site problem, and we get an effective local action that we treat with two different approaches. First of all, we apply a continuous time Monte-Carlo simulation, which is an exact but numerically expensive method. So we are only able to apply this in the low temperature phase. In order to gain access to the properties of the glassy phase, we have to apply another approach, an iterated perturbation theory. And we will do just that. Before presenting you the results, let me make a quite technical digression. I just would like to give you some idea about how this mapping to a single site problem works. But if this is too technical, don't worry, I will return to the physical properties of the model very soon. So I would like to illustrate this mapping to a single site problem by applying the so-called cavity approach. Our goal is to obtain an effective action for the site 0 and to integrate out all remaining sites from the original lattice Hamiltonian. In order to do this, we divide our action into 3 different terms. The first term is just a term that involves the site 0. The second term consists of 2 parts. This is the part of the action that connects the site 0 to the rest of the system. The first term here is the nearest neighbor interaction, and the second term here is the hopping. And finally, we have the part of the action that doesn't involve the site 0 at all. This is this si not equal 0. So if we rely on the limit where z goes to infinity, we can actually exactly integrate out all sites except 0. And let me just very briefly present to you the outcome of this calculation. So we get an effective local action for site 0. The first term, of course, is just the original term in the action that involved the site 0. And now we get additional terms from the expansion in these two terms that connect the site 0 to the rest of the model. So the first term comes from the term that is quadratic in this hopping part of the action, and this gives rise to this term here. What we have here is the sum of some local Green's functions, but these Green's functions are not exactly the original local Green's functions of our model. Instead, these averages are so-called cavity averages, they are evaluated with respect to this remaining action Si not equal 0. So they are calculated in the absence of psi 0. Okay, so we get this term from the square of the hopping term. Similarly, we get a term in the effective on-site action from this nearest neighbor interaction. So basically, the interaction with the neighboring sites introduces a Hartree shift into the energy, into the on-site energy epsilon I. And this Hartree shift includes the cavity averages of the occupation numbers delta and I. And finally, we also get a term from the square of this nearest neighbor interaction term, which is depicted here. And it depends on the local density-density correlators, more precisely on the cavity density-density correlators. So this is kind of the local action that we get. And now we can make further progress by saying that, okay, so here we have basically local cavity Green's functions, and we sum over infinitely many such Green's functions here. So let's just forget about the fact that these are cavity averages and substitute this sum just by the average local Green's function of our lattice model, G tau. This is done here. Similarly, in this term, we just say that we forget about the fact that this is a cavity average, and we will just use instead the average density-density correlator, chi tau, in the action. So finally, we actually have this Hartree shift, but we can combine it with the random on-site energy epsilon naught to get some renormalized energy epsilon naught theta. So if you think about it, epsilon naught was originally a Gaussian random variable. Now we are adding to that infinitely many Hartree shifts. So by central limit theorem, it seems like a natural assumption that this variable here also has a Gaussian distribution. And then what we get is a new energy epsilon theta, which still has a Gaussian distribution and includes the effect of all of these Hartree shifts. So by this cavity approach, we can arrive at this local action. And what we have, in fact, is not just a single action, it's an ensemble of actions depending on this random site energy epsilon theta. Of course, this epsilon theta has some field distribution. I have just argued that the natural assumption for this is that this field distribution is simply Gaussian. So we have to solve these ensemble of actions actually self-consistently because the action contains as parameters the average Green's function and the average local density-density correlator of the model. Okay, so this is the end of the more technical part. I just wanted to illustrate how this calculation works. I just would like to make a final remark. So actually, what I just said is a bit oversimplified. At low temperatures, things become slightly more complicated. The reason for that is that at low temperatures, one can have spontaneous symmetry breaking. For a ferromagnet, we would just have two symmetry broken states, a ferromagnetic one and one which has reverse magnetization. But in this case, the situation is even more complicated with many different symmetry broken cases. And in the cavity approach, we have to be really careful to incorporate all of them. But nevertheless, this can be done, though I won't go into the details, and it can be conveniently done through this so-called replica trick, just for the experts. I mentioned this. But the outcome of this work calculation is that we can still map our problem to an ensemble of effective local actions, which basically looks exactly as the action that I obtained before, sorry. So it has as parameters the average local Green's function and the average density-density correlator. And it also depends on some effective local field epsilon theta. And this local field, of course, has some distribution P epsilon theta. We have to solve these ensemble of actions self-consistently. So for example, to get G tau, we have to calculate the epsilon-dependent Green's function of this local action, and then we have to average it with respect to this field distribution P epsilon theta. A similar approach works for the density correlator. Now, where is the glass transition in this model? Earlier, I argued that the natural assumption for this Hartree field distribution is that it is Gaussian, And this is true in the high temperature phase. In this case, the effect of interactions is rather trivial. They just renormalize the variance of this Gaussian distribution. However, it turns out that things become more interesting at low temperatures. And instead of a Gaussian distribution, we find a very different shape. And actually, this Hartree field distribution displays a pseudogap behavior, which is very reminiscent of this Efros-Shklovskii scaling that I was showing to you earlier. Before going further, let me just show you the phase diagram. So here is the phase diagram that we obtain. At high enough interactions, we get an electron glass phase where this field distribution is not Gaussian. So this electron glass phase is governed by the interactions. So we always get that if the interaction is strong enough. And this glassy phase can either be melted by thermal fluctuations by increasing the temperature, or by quantum fluctuations by increasing the strength of the hopping. One other thing that I show here is the density of states at exactly the phase transition. And you see some dip in the density of states at the Fermi energy. And this dip already shows you that some pseudogap behavior is going to happen if we go into the glassy phase. And it is the presence of this gap is the consequence of the repulsive nearest neighbor interactions. So in order to obtain this phase diagram, we, as I already mentioned, we applied two different methods, some continuous time Monte-Carlo method and an iterated perturbation theory. I won't go into the details now. I would like to mention that here I show two cuts of the phase diagram calculated with the two methods, and we get results that are very, very close to each other. So we can use this so-called continuous time Monte-Carlo method to validate our iterated perturbation theory. Okay, but I don't want to be too much over time, so I will skip this part now. Let me go to the properties of the glassy phase instead. So here we cannot use the quantum Monte-Carlo simulation anymore, at least not right now. What I will show you are perturbative results. Okay, so first let me show you this field distribution P epsilon. I argued that this shows you the presence of the glass transition. And this is depicted here on this figure. So this figure here shows this local field distribution at various temperatures. At high temperatures, we get a Gaussian shape. And this is even true at the critical temperature depicted by this dashed line here. So this is what one would expect naively. However, if we further decrease the temperature, then we see that the probabilities at small fields get suppressed, and there is this so-called pseudogap opening in this distribution P epsilon. Moreover, one can show that deep in the glassy phase, one finds an Efros-Shklovskii universal scaling for this field distribution function. So P epsilon at small fields is actually proportional to epsilon divided by V squared. This is exactly the same as the Sherrington-Kirkpatrick spring glass result. So this scaling is shown on this figure here. The main figure just depicts the field distribution for different interaction strengths, and then the scaling collapse is shown in the inset. So after proper rescaling, all data collapse to a single curve. So we get this Efros-Shklovskii scaling, and one important point is that the slope of the universal scaling function is 1 over V squared. So it only depends on the strength of the interactions, showing that this phase transition is really driven by the interactions themselves. It is structural in this sense. So just very briefly, we got this pseudogap behavior and there's this local Hartree distribution, but that might seem like an artificial object to you. But instead, we can recover the same scaling function by examining the density of states, which is also experimentally accessible in tunneling experiments. So we get a similar Efros-Shklovskii scaling. Rho omega at small omega is just proportional to omega divided by V squared. This scaling collapse is shown on this figure. So the main figure shows that just the density of states at different interaction strengths, and the scaling collapse is shown here in the insert. What you see with this dashed line here is the classical scaling function. So that's just the scaling function one gets if one sets this hopping t to 0. And what you can see is the quantum scaling function and the thermal scale, the classical scaling functions are really similar. They have the same slope, 1 over v squared. However, these two scaling functions are not exactly the same, pointing to a slight difference between the roles of quantum and thermal fluctuations. Okay, and then there is one last thing that I would like to mention, and this is that we can even take a closer look at the order of the phase transition with our method. In particular, we can evaluate the free energy density of our original Hamiltonian. And by taking the derivative of this free energy density with respect to the temperature, we can evaluate the entropy of the system. And we can examine the temperature dependence of this entropy. Now, what I should mention that you should take these results with a grain of salt because very high precision is required for these calculations. And now we are relying on a perturbative approach. So of course, we can never be absolutely sure about our conclusions, but nevertheless, this is what we get. Okay, so on the left-hand side, you see what we get in the classical case. So this is just basically the case when the hopping is 0. So we have a Sherrington-Kirkpatrick model at hand. With dots, you see a solution obtained within the assumption that the distribution of the Hartree fields remains Gaussian. As I already argued, this assumption is actually wrong at low temperatures and leads to an unphysical solution, which is very clear from here since we get a negative entropy at low temperatures. These crosses show the real physical solution, and that goes to 0 as t goes to 0, as it should. And this entropy is completely continuous at the phase transition, which is here, showing that the phase transition is at least of second order. Now we switch on the hopping on the right-hand side and basically do the same thing. And here we get something very different. So these crosses tend to show that at the critical point, we see a jump in the entropy. So this figure would suggest a first order phase transition. And it is really important to decide the order of the phase transition, since, as I mentioned, many calculations are based on the Landau approach, and those calculations assume a continuous phase transition. So this is a question that should be further investigated. Okay, so this was basically the last thing that I wanted to mention, and I'm already a little bit over time, so I would just stop at this point with my summary slide, and I'm very happy to take questions if you have any.
Okay, Izabella, thank you very much. If you want to go through your summary, I think it's fine. It doesn't look that long, and then you can take questions. Okay, so maybe I would go through the outlook. So of course, one very interesting thing to do would be to enter the glassy phase with the continuous time Monte-Carlo calculations, which is a numerically exact method. We are trying to do that now, so this is a work in progress. And then there are very important open questions. So for example, I didn't talk about the role of spin degrees of freedom at all. This was a spinless model. And I talked about a mean field model in infinite dimensions in some sense. So this is certainly very valuable to have this exactly solvable model. But it would be interesting to examine actual Coulomb glasses in 2 and 3 dimensions. And of course, one open question is the dynamics. I didn't talk about dynamical phenomena, anomalously slow responses. But with this, I think I can finish and take questions. All right, thank you. Any questions?
Well, I would have a question. Hello?
Yep.
Yeah. Do you put in the disorder on site, right?
Yes.
So it's like a chemical potential, which if you put in the disorder on the bonds, so you would have a disordering of the nearest neighbor hopping. Could you get the same type of physics, or would it not?
I think it is important to have repulsive interactions, probably.
But you could keep the repulsive interaction, but add some disorder not on site, but to add some disorder on some disordering on the bond.
Yeah, I just meant that. Okay, so if I Oh, you mean in the hopping term, not in the interaction term?
So the hopping term would be the plain hopping term?
Yeah, I don't think it matters too much actually, in the sense that as I tried to argue, this is a structural transition governed by the interaction. So actually, I just can take out any disorder from this model, and I would still have the same physics. So based on that, I wouldn't assume that that disorder makes a large difference, but I'm not sure, to be honest.
Because if you take disorder as like the one I was suggesting, like on the bond, then you can do that with Monte-Carlo. There's no sign problem.
Okay, so actually, I think that the situation is more, maybe more subtle than that, because in the original Hamiltonian, it's true that you are at half filling, but once you perform this mapping, you actually always add these fields here. So you have to solve an ensemble of actions, and in this ensemble, you have to solve this ensemble in the presence of this external field. So if you take this G epsilon theta, that is not at half filling anymore.
But what I was suggesting is to, if you go back to your first slide, not do DMFT, but really solve this problem in finite dimensions on a lattice, right?
Okay.
My only claim is that if you say that the random on-site potential could be replaced by a random bond potential, then which would randomly change the hopping, and you would still keep the same physics. That's the question. Then you could solve this.
I'm just saying that I think you don't even need to put randomness into the hopping, actually, because even without that, you have this transition. So here you can actually set these epsilons all to 0, and you still have the same physics. One way to say this is to consider the limit where the hopping is 0 and also this epsilon naught is 0. And then you can actually show that once you perform this mapping to a single site, you get exactly the same action as in the Sherrington-Kirkpatrick model in 0 magnetic field. So that's exactly the Sherrington-Kirkpatrick model, and it has the same transition.
Okay.
All right. So if you don't have further questions, we can of course use the time of the break and of the asynchronous time afterwards in late afternoon. I guess we could go to the next talk. I'm going to stop the recording. So thank you again.